welcome to week 2 of Statistics 2. The first week was largely recap of basic probability, the foundations of the theory and definitions, and some interesting relationships between data, statistics, probability, and things like that. Hopefully you had a good time reading up things around the week 1's content. Hopefully you're now ready to jump on. And second week also is sort of recap. We're going to look at discrete random variables. This is again a topic you've seen before in Statistics 1. So we'll go through it at a reasonably fast pace, but at the same time, hopefully this is a good recap for you, and so that all notation and everything is reasonably well set in this course as well. Okay, so let's get started. Okay. So I'm going to motivate the idea of a random variable and why you need it and all that. And let's go back to this experimental setting of the IPL Powerplay over, right? So we've been thinking of the 1 over of an IPL Powerplay innings as our experiment. And the outcome itself, if you look at what happens in a Powerplay over, there's so many things that can happen. So here in this little table here, I've shown you the first over of a few games and a few teams that played it, and you can see there are several deliveries. Sometimes there are 6 deliveries in the over, sometimes there are 7 deliveries. If there is like a no ball or a wide or something, then you have 7 deliveries, and every delivery there's a run or there's no run, and when there's no run there could even be a wicket, right? So all that is not necessarily captured, and the outcomes are of various types. You may want to know where the batsman hit the ball, this, that. So there is the actual things that happen. For instance, the speed of the delivery, who's the bowler, who's the batsman. So much you can ask about what happens during the power play over. It's a complex experiment. There's lots of things happening, right? And to even write it down in a reasonable way, you need, if you remember from last week, you need like an YAML file and this, that, and it's a very complicated way to put it down. And what I put down here is a simplified spreadsheet version of it. But nevertheless, you can see it's a lot of things happen during a power play over. So when you're looking at a complicated event like this, so one always tries to see if you can simplify things a little bit, right? So don't worry about the entire outcome. Is there some particular aspect of the outcome I am interested in? So for instance, several numerical values you're noticing here are of interest here, and it's always good to think of numbers or some smaller outcome set as opposed to a much larger complicated detailed outcomes. Okay, and random variables basically allow you to do that, right? So these are numerical values which are computed from the outcomes of the experiment. Typically people will say numerical values, think of random variables always as taking a number, but you can also have some other finite set. If it's only like heads or tails, you might as well have heads, tails as opposed to 0, 1 or something like that. But one can always associate a numerical value with any set, and then so that way numerical values are interesting to consider. But naturally in experiments like this, several numerical values show up, right? You see that number of runs in the over may be of interest to you, number of actual deliveries in the over may be of interest to you, number of wickets, number of boundaries, number of dot balls, and there are some connections between these numbers, but nevertheless they are all numbers, and they can be they are objects of interest, and they can be more readily and easily understood than the entire detail of what happened in the over, right? So it's a more complicated occurrence. Okay, so keep this picture in mind. So as we go forward, we will simply describe random variables. We'll say this is a random variable, this is the distribution, this is the PMF, etc., etc. But don't lose track of the fact that this random variable is bringing out one aspect of maybe a very complex experiment, and then you want to define different random variables, understand them, etc. So this is sort of the big picture behind how and why random variables are very, very useful in probability. And you will see as we go along, most of the time we'll be dealing with random variables, right? So I know we spent a lot of time putting down the theory and the notion of sample space, events, probability function, etc., etc. But most of the real action when it comes to applications, or when it comes to even working out things, everybody uses random variables. So random variables are an extremely powerful tool. They come as one aspect of the basic theory, but they end up being very, very powerful. So it's important to know, have comfort in dealing with random variables, how to express the distribution of the random variable, what is the range of the random variable, what is the PMF, particularly for discrete random variables, what is the PMF, how to work with random variables, how to compute probabilities of events with random variables, how to manipulate random variables. All these things are very, very important skills to pick up in this week's content. Okay, so let's get started. Hopefully this definition and this motivation was clear to you. Let's jump into the definition of a random variable. Okay, so here's the definition of a random variable. So if you remember, we have a probability space, which is, there's an experiment and there are outcomes. And there's a sample space which contains all the outcomes, a set of all possible outcomes. And typically, this is the definition of a random variable. Random variable is a function with domain as the sample space of the experiment, and the range is the set of real numbers. Okay, so it takes the outcome to a number. Okay, so I'm saying number. Some of the definitions you will hear from in some books, they won't necessarily ask for a number. They will let it go to some other set also. But in this course, mostly and most of the time, random variables of interest always take you to a number. So we will stick to this definition. There can be a slightly more general definition where the range is not a number, but some other set also. But I think having it as a number is good enough for most cases. So we'll stick to that. Okay. So a random variable is a function from the sample space to the numbers. Okay. So random variable is going to take an outcome and map it to a number. Okay, so just like the previous example we saw. So that's a random variable. There is a technical condition. I will describe that soon enough. The function needs to satisfy some property, but it's mostly not very important to us. Okay, so here's an example. Okay, I have an experiment. I'm tossing a coin. The sample space is h comma t, isn't it? Heads and tails. Now I can have a variety of random variables here. I can have a random variable x, which maps h to 0 and t to 1. That seems like a natural and simple way to define the random variable, and that's not necessarily the only random variable, right? I could come up with a random variable y, which takes heads to -10 and tails to 200. Now, why you may do that may or may not be relevant here. As far as the definition is concerned, it's a valid random variable, right? It's not wrong. Or I can get more fancy, use some really fancy numbers. I can take a random variable z to be mapping h to √2. And tails to maybe pi or e or some other fancy number that you can think of. Or you can have a very trivial, silly random variable which maps everything to 0, right? I can do that as well. So all of these are random variables. So you see, I'm defining various types of random variables from the same sample space. Okay, so usually, like I said, people would think of meaningful functions, not for the heck of it. Nobody would do √2 pi and all that. So usually some meaningful functions are considered. If you ask me, the most meaningful looking function in this whole thing is probably x, isn't it? One more thing I should warn you, this while random variable is a function from the sample space to numbers, usually we'll forget all that and we'll focus only on the values the random variables take. Okay, so this x of h, x of t and all, people will drop the of t, of h notation. They'll simply write x. Okay, so quite often the notation will say x equals 0, x equals 1. You will even forget in your mind that the random variable is actually a function from the sample space to numbers. Okay, so keep that in your mind. It's something that we will also quickly do, but the definition is that it's a function from the sample space to the real line, and you've seen a few examples here. Okay, let's continue to a slightly more complicated and maybe a more illustrative example, which is throwing a die. Okay, so I'm going to throw a die, and the sample space is 1, 2, 3, 4, 5, 6. Right? So this has been sample space we've defined here. How do you want to define a random variable from this sample space to the real line? You can, so I'm giving you a generic way to do it. What is the generic way to do it? You pick 6 real numbers of your choice, okay, whatever they are. Okay, let's call them x1, x2, x3, x4, x5, x6. Okay, and I can simply say my x will take 1 to x1, 2 to x2, 3 to x3, so on. Okay, so that gives me a random variable, isn't it? This is like the most generic random variable mapping to the real line that you can think of. Okay, so what values do you pick for x1? What values are interesting, right? So technically you could do anything, right? So like from a definition point of view, you don't violate the definition. You can pick any value. Okay, but maybe some types of values are interesting to consider. One type of value is the xi's could be distinct. What do I mean by distinct? No two of them are the same. Okay, they're all different. Okay, so then in that case, this random variable simply is like a 1-to-1 function from 1, 2, 3, 4, 5, 6 to this other number. Okay. Now, essentially this is the same as the sample space in this case, right? So 1, 2, 3, 4, 5, 6 is 1, 2, 3, 4, 5, 6. So you can have a random variable which sort of mirrors the sample space. Okay. You have outcomes which are maybe not numbers, maybe something else, but you can sort of mirror the sample space and map it to one number. Okay. So you could do that. That could be a choice that you would do. In that case, random variable sort of represents everything that can happen. So usually that is not done. Usually what's done is something like the second example here, need not be distinct. I might want to have a random variable which just tells me whether the number is even or odd, right? So in that case, what will I do? I only need two numbers, isn't it? If the outcome was 1 or 3 or 5, I will say this random variable E takes the value 0. If the outcome is 2 or 4 or 6, I will say that this random variable E takes the value 1. Now this random variable E now has a different sort of a meaning. It tells me whether the number that came out is even or odd. Okay, so this is not mirroring the sample space fully. It's sort of making it a proper function of it, a different type of a function. Okay, so hopefully you see this example. Think about it. So the way the definition goes, it seems like it's anything, but usually people pick up something of meaning and assign the value suitably to the outcomes. Okay, hopefully that was a reasonable example. Okay, so now what's crucial is using random variables, you can define events. Okay, so what are events we saw before? Events are subsets of the sample space, some subsets to which we associate probability. Correct? So that's the crucial idea. For every event, you have to be able to associate a probability. So we define events in that fashion. Right? So events generally are subsets of the sample space and meaningful subsets. Right? So subsets that bring out some occurrence of something that is interesting to you. Right? So that those are events. Okay. Now, if I have a random variable, I am mapping every outcome to a number. Now, using that, I can define some interesting events. Okay. So notice, give an example here. There's this example which says, I can say, now I'm going to look at the event that the random variable capital X is less than small x. Okay. So that's an event which is of interest. Let me see if I can find my laser pointer. Okay. So notice this event here. This is the event I'm talking about, right? Notice how it becomes an event. Okay. So at this point, you may even suspect, why is this an event, right? So I'm just having something which says random variable X is less than small x. The reason is this is basically representing the set of all outcomes, right? Remember, random variable is a function from sample space S to the real line. If I say now the random variable X has to take a value less than small x, then the outcome that occurred must be such that X of S is less than X, isn't it? Right? So one of the ways to visualize this, if you want a visualization, is the following. Maybe I'll change my color to blue. Okay. So let's say you have the real line. Okay, so this is the real line, and your in the example here. So for instance, you could have the random variable x of 1 here, x of 2, so on, right? So you may have x of 6 here. Okay, and I may look at a small x here. Okay, and if I say x is less than small x, I'm talking about everything to the left of x, and whatever outcome that is captured here is something that belongs to this event x less than x. Okay, so that is what is given here. Okay, so that is exactly what's given here. The set of all, the set x less than x, the event x less than x is actually a subset of the sample space. It contains all outcomes which result in the value of the random variable x being less than that small x. Okay, so this has to be this is an event. Okay, and it has to be an event. So this is, you remember there was a condition I mentioned that the random variable, the function should satisfy a condition. This is sort of like the technical condition. Okay, so let me not go into more detail than that. This is enough. So this is a very nice and important connection. So I kept telling you that eventually we'll come to a point where we'll only worry about random variable, right? We won't go back to sample space and too much of that. Usually it's not done. This is the reason why people don't bother too much about doing other things. The reason is, once you define a random variable which is meaningful, using that random variable, you can define events, and using that you can take care of everything that you need to take care in the probability space. Any calculation you can do it in the language of random variable. So, it is a very powerful notion. So, notice now if x is less than x is an event, then the complement of that is also an event. What is the complement of that? X is greater than or equal to x, okay, isn't it? And then you have to think of unions, intersections, etc., and all these things will also become events. Okay, so these are not very difficult to look at, and you will see that all these guys are basically different ways of defining events using random variables. Okay, so you take a random variable and you define have a small x. You can do this. In fact, you can do a little bit more. You can even have events of this type, right? So you can have you could have things like x less than capital X less than x1 less than x2. Okay, so this is an event. Okay, so you can have so many other possibilities here for event. Okay, so this is another possibility. Okay, so you can do all this. So once you have a random variable, using the range of values or limiting the range of values of the random variable to a particular interval or a subset or any other thing gives you an event. Okay, that's what's nice about random variables and the connection that they give to events. So once you understand the distribution of the random variable well, you can keep finding probabilities of events and all. Okay, so keep that in mind. So here's an example. Once again, I've given you an example where the random variable is sort of like the identity function in throwing a die. Okay, x is simply the number that shows up there. You can see x equals 1 is the event that die shows 1, x less than 4 is the event 1, 2, 3. Any event can be expressed in terms of x. Notice this is a crucial sort of property, because this x is like an identity. It's a mirror of the sample space, right? Okay, it's a mirror of the sample space. So any event that you possibly have in the sample space, you can define it using x in this fashion, right? For instance, here is a trivial way to do it. So it's sort of like a trivial thing to say, but it's sort of important. Okay, so that's why you can worry about random variables and little else. This is really needed most often. Okay, so this is a simple example that we looked. Okay, here's a slightly different example where we've used this random variable e that we defined on the throwing of the die, right? 1, 2, 3, 4, 5, 6. I had this random variable e, which said for 2, 4, and 6, I have the random variable take value 1, and for 1, 3, and 5, it takes value 0, isn't it? So if you want to picture the real line once again, it's good to picture it on the real line. Picturing random variables on the real line will give you some idea. So there's 0 and there's 1. This is E of 2, E of 4, E of 6, and this is E of 1, E of 3, E of 5, right? So I'm writing all this out in detail, but eventually you don't have to write it. You'll sort of see how things work out. So E equals 0 is the event. Oops, I got it wrong, did I? So I mixed it up. So let me just redo this. So this is E of 1, E of 3, E of 5, and this is E of 2, E of 4, E of 6. Okay. So if you look at the event E equals 0, this event is simply 1, 3, 5. This event is E equals 1 is 2, 4, 6. Now notice this event E less than 0. So if you say E is strictly less than 0, right? This is E less than 0. Equal to 0 is not there, less than 0. So that's the null event. Nothing is there. On the other hand, if you say from here, if you look at say E less than, I don't know, 1.2. Okay, so it says E less than or equal to 1. If I say E is less than 1.2, I have everything captured, right? So everything is possible. Whatever happens, E would be less than 1.2. Okay, but notice if I have events like 2, 5. Okay, so what happens to this event? You cannot express it purely only in terms of cannot be expressed in terms of E, isn't it? So think about this point. So that's the reason is E is not like a mirror of the original sample space. It loses something, isn't it? It only represents whether it's even or odd. So if you put 2, 5 as an event, just the value of E is not going to tell you anything, right? So you can't be sure about these kind of events. Okay. So you can have random variables like this. So you may have random variables that capture the entire sample space. You may have random variables that capture only some aspect of the sample space, and they are useful still. That's how we work with experiments in practice most of the time. Okay. So hopefully these few examples are giving you a rough idea of how random variables are defined. They are necessarily, I agree, there's a simple examples, but you have to start small and slowly build up on more and more complicated examples. Okay. So I'll leave you with this thought on why random variables. This is the first part of defining random variables. You may wonder, why do you need random variables? We already know the samples, etc. So if you look at the IPL Powerplay over, when you look at complicated outcomes, where there are lots of things happening, you usually get lost trying to assign probabilities to outcomes, right? So remember, when you want to do probability space calculations, you want to assign probabilities to outcomes, and when the outcomes are itself so complex, it's very hard to assign probability to that whole outcome, right? And then you're thinking of all sorts of complicated stuff. It doesn't work. Okay, what is easier is to start defining a bunch of random variables that you can study. Okay, so number of runs, number of runs scored in first ball, number of runs scored in second ball. You can have random variables like that. You can have so many random variables defined, and then you focus only on the finding out the distribution of the random variable. What is the events around the random variable? Just when I say distribution of the random variable, that's what I mean. How to calculate probabilities for events defined using that random variable. Just focus on that. Okay, don't worry so much about the entire outcome itself. Because the outcome itself is too big. You may not have enough data in practice to do anything reliable with that, right? So that was also a problem. So you think of a smaller aspect of that whole outcome, which maybe doesn't capture everything that happened, but gives you the important information that you want. And more importantly, in practice, you have enough data to meaningfully say something about that distribution. Okay, so this is why people work with random variables in practice. They are easier to assign probabilities to and easier to work with because you can look at the data and then sort of motivated by that, meaningfully assign probabilities for random variables. We'll look at all these kind of aspects going forward. It's definitely a more complicated notion than what you were used to in statistics 1, but keep this aspect in mind. So in practice, most of the time when you apply probability, you will be working with random variables, right? You'll be directly working with random variables. So you will have this big experiment that's going on to generate the random variable somewhere in the back of your mind. The more you have that connection in your mind, the better you will be in translating things to practice. But the felicity to use random variables, the skill that you need to develop in manipulating random variables is extremely important, and we'll focus on that a lot in this course as well. Okay, so this is the end of the first module. We'll go to discrete random variables and their distributions in the next one.